Welcome to the Crazy Hat Chemist. So here we go with another awesome video. This one is going to be my chemical reactions worksheet, a stepwise solution to all the problems on chemical reactions. So before we get into this, I'm going to make the assumption, and if you haven't already done so, then you need to be following the following things, following directions. That is the following. You need to go to my YouTube channel. That is the Crazy Hat Chemist. And you are going to go to the nomenclature unit. And in the nomenclature unit, you're going to follow all of the videos in the nomenclature unit, follow that playlist, and make sure that you understand everything in nomenclature. You can't do this unit without nomenclature. Furthermore, the other thing that you're going to do is you're going to go to the chemical reactions playlist on my YouTube channel. And you're going to make sure that you watch all the videos in the chemical reactions playlist prior to going through this worksheet. In addition to that, I'm assuming a number of other things as well. Number one, you have a periodic table. I will be using this one. This is from the SAT subject test, SAT 2 subject test in chemistry, and hopefully they bring that back. So I will be using this, but you can use any periodic table. In addition to that, I will assume that you know your charges on ions and oxidation numbers. Some of those are based on your periodic trends on the periodic table, and other ones are based on some systematic nomenclature and also knowing your polyatomic ions by heart, or you have fully memorized the polyatomic ions. So I'm assuming that you know your polyatomic ions, you know the periodic trends. I'll go over many of those. In addition to that as well, I'm going to assume that you know your solubility rules as well. Okay, right here are the solubility rules. These are the solubility rules of which I have designed. So hopefully you have a copy somewhat similar to that. And without further ado, let's get started and hammering this out, so that you can have a full grasp of the understanding of everything here on chemical reactions. All right, so let me put my little weight down here so that I don't move my paper around too much. All right, here we go. I'm going to read the directions. It says, directions: determine the formulas of the reactants and their states of matter. Refer to the solubility rules. I just aforementioned that. Then, from the reactants, determine the type of reaction. There are 5 basic types of reactions. There's double displacement, single displacement, combustion, combination, and decomposition. From the type of reaction, each type has a unique set of characteristics and patterns. Determine the products and their states of matter. And finally, balance the reaction. Note: assume that all the reactants yield products for the purpose of this worksheet, except for single displacement reactions, where you must consult an activity series to determine if a reaction will occur or not. In addition to that, I'll make one other note on the balancing of the reaction. We're going to make the assumption, like most chemistry teachers, instructors, professors do, and that is the following. We're going to have whole number stoichiometric coefficients for balancing of equations. So that's going to be really important here. We are not going to end with any fractional coefficients. Okay. All right. So without further ado, let's just plow right on to this first problem here. So this first problem, it says a solution of sodium nitrate. So I'm going to circle words that are important and underlined words that are important. Sodium nitrate is obviously important. A and of don't really matter. Is added using a pipette. Who cares how you add it? But plumbous oxide is important, and it doesn't matter if it's a test tube, a graduated cylinder, or a beaker, or whatever it is that you put it in. So we have to figure out the formula for sodium nitrate. And this is partially coming from a periodic table and your periodic trends. And so here are some of the periodic trends. Okay, so let's see here. Here we go. Periodic trends. This is the alkali metals from lithium through francium. Those are the alkali metals. Hydrogen is in the same column, but it's not an alkali metal. It is in group 1. This is group 1, the alkali metals. These have periodic trend charges of a 1+. Group 2 has periodic trend charges of 2+. Okay, and then we have a 3 plus, a 4 plus, a 5 plus, and I'm going to note something here. What's the Roman numeral for 5? Oh yeah, that's right. Absolutely. That is a V and a V, and that is a 5. All right, fantastic. And then after you hit 5, so 1, 2, 3, 4, 5, then you're going to count another 5. 1, 2, 3, 4, 5. These 5 elements right here have 2 different charges. They are a 2 plus and a 3 plus. Okay. And when we get into this a little bit more, we're going to have either a Roman numeral of a 2, a Roman numeral of a 3, or you can go by the common nomenclature, which I typically do in my instruction, and that is chromus or chromic, or ferrous or ferric, or Nicholas and Nicholic. So the OUS ending always goes with the lower charge, and the ic ending always goes with the higher charge. Now, you've traveled 1, 2, 3, 4, 5, and then you've done another 5, and each of these have 2 different charges, whereas these only have single charges. Then, because you've been traveling so fast, you see some lights in your rearview mirror, and that is what? A copper. Copper is going to make you slow down. You've been traveling at a speed of 2 and 3, so copper's charges are 1 and 2. And this is the OUS, and this is the ic ending for copper. That's cuperous is a 1 plus, cooperic is a 2 plus. Then we have a diagonal pattern right here, and that is silver, zinc, and aluminum. And that is our diagonal pattern right there, and that's a 1, a 2, a 3. Then there's a continuation of this diagonal pattern, and that zinc and cadmium are in the same column, so they're both 2 pluses. All right, and then we have gold. Gold is in the same column as copper and silver, so they have a common charge, and copper has a 1 plus, silver has a 1 plus. Therefore, gold will also have a 1 plus. Gold is worth more, so it's going to have the highest charge of any of these, and the silver only has a single charge, but the copper has a 1 and a 2, so gold must have the charge of a 3 plus. By the way, it's just for memorization, but gold has a 3 plus, not because it's worth more, not at all, nothing to do with that, but just a way to remember it. For mercury, there are 2 different charges on mercury, and one of them is a 1 plus, that's mercurous, and then a 2 plus, and that's mercuric. But there's a funny thing that happens here with mercury, and they both of the mercury charges are actually a 2 plus in combination with that ion. So I'll go into further detail as we walk ourselves through that. Then we have a combination of 2, that's right over here, that's tin and lead. Both tin and lead have 2 similar charges, and they're both a 2 plus and a 4 plus, okay? Then we're going to slam all the way over to the right-hand side of the periodic table, and right up here, these are the noble gases. They don't form compounds for the most part, at least with ionic compounds, so we're not going to worry about those in this unit. Then we have the halogens, which is fluorine, chlorine, bromine, and iodine, and those have a periodic trend charge of -1. And then oxide and its column, -2, nitride and its column, and -3, and carbon has a -4 or a +4, depending on where it is. Okay, and then if we look at these top columns here, 1, 2, and then we're going to skip the transition metals, and we're going to go for a 3 plus in this column. I'm hoping that you remember that there is effectively on many periodic tables an orange staircase line that separates the metals from the non-metals. And the non-metals are over here on the right-hand side, the metals are on the left-hand side. So that's why the non-metals typically have the negative charges because they want more electrons, and the metals have positive charges because they want to get rid of electrons. All right, so coming back to the problem of which we have at hand, and we have the compound sodium nitrate. So sodium, it's in group 1 or an alkali metal, so it has a 1 plus charge to it. So that is going to be Na1 plus. And then you have to know your polyatomic ions in order to get this next one here. And the ammonium ion is the only polyatomic cation. The only polyatomic cation. Notice I have on this left-hand side all the cations. There's only one of them. The rest of them are slammed on the right-hand side, and these are the polyatomic anions. And nitrate is right here. It happens to be one of them. So that's NO3 minus 1. So hold on just a second here. That's NO3 minus 1. All right. And then what we're going to do is make that compound. All right. Fantastic. So now you have sodium nitrate. Now we're going to move on and get plumbous oxide. Okay. All right. So we're going to go back to our periodic table and the periodic trends of which I just mentioned. And plumbic and plumbous is from lead. So we're going to flip over here and we're going to go, what is this? This is plumbous. So plumbous is the lower charge of the two. Like I had mentioned, the lower charge has the OUS ending. The higher charge has the ic ending. So the lower charge for lead is a 2+. So it will be lead with a 2+. And then oxide is right here, and that's a 2-. So these are based on the periodic trends. So plumbous is Pb2+, oxide is O2-. And this is how we work with this. We're going to take the absolute value of the two numbers here, the cation and the anion, and we're going to take the bull by the horns and flip it. And so what I tell my students is, you got your bull by the horns. This index finger is the 1+ charge. This pinky finger is the 1- charge. You're going to take the bull by the horn, flip the numbers, and drop it down. That will give you this number coming here, this number coming here. So you're going to have Na NO3, and then we're going to have a parentheses because we're going to write the state of matter there after that. We're going to do the same thing for the plumbous oxide. We're going to take the absolute value of these two numbers, flip them, and bring them down. And what we get is an intermediate step as Pb2O2. And one of the rules here on writing formulas of chemical compounds is that you must use the lowest whole number ratio. So the lowest whole number ratio. So you can see that 2 goes into 2 one time, 2 goes into 2 one time. So this is going to be PBO. So it's going to be plus PB and O. And I'm going to leave space there for the state of matter. We're going to draw an arrow. So on this left-hand side of the arrow are called the reactants. So these are the reactants. On the right-hand side of the arrow will be the products. And hopefully that makes sense. Reactants react, products are produced. So what we need to do now is figure out the type of reaction, okay? And the type of reaction is based on how I put these formulas together and how they're organized. So I have a cation and an anion, and a cation and an anion. This is characteristic of what's called a double displacement or a double replacement reaction. So I'm going to write DD or DR here off to the side. So it's a double displacement or a double replacement, okay? With a double displacement or a double replacement reaction, you're going to also, on the product side, have the following pattern of a cation anion and a cation anion. So what we're going to do to write the products, we're going to combine the cation of the reactant with another alternate anion than what it is combined with on the reactant side, and that would be the oxide. So we're going to take the same kind of concept as take the absolute value of these two numbers, take the bull by the horn, flip, bring it down, and we get Na2O1, but we don't write the ones. We're going to leave some space to write the state of matter. Then our other compound on the product side, we need a cation and an anion. And the cation is written first, then the anion. We're going to take the absolute value of these two numbers and write that down, and we're going to get PB parentheses NO3 and a 2, and we're going to give ourselves some space for that state of matter as well. Notice that I put parentheses around this polyatomic ion. So anytime you have more than one of a polyatomic ion, you're going to need the parentheses. This 2 distributes over all the terms within the inside of the parentheses, just like any kind of math problem, because this is just really an applied math class. Okay. All right, now what we're going to do is we're going to consult our solubility rules, and from our solubility rules, we're going to get the states of matter, which go inside these parentheses right over here. So, sodium nitrate. So what we've got is sodium nitrate. They are soluble. And then we're going to follow this arrow. Are there any exceptions making it a precipitate or a solid? There are no exceptions. All are aqueous. So doesn't matter if it has sodium or nitrate. That means any compound with sodium, any compound with nitrate will be aqueous. Okay, our next one is plumbous oxide. And I cannot find here at the top of this any of the lead or the oxide. So what we're going to have to do is look to the lower section of my solubility rules, and I've divided them up. I want you to notice one thing that's very critical here, and that is this top section. All the arrows are going to the right. On the lower section here, the single arrow is going to the left. So you read it in the opposite direction, and that is oxides are precipitates. Exceptions to this are ammonium ion and the alkali metals. Alkali metals are group 1 effectively, except for hydrogen. So oxides are insoluble compounds, of which lead is not one of the exceptions. So that means that this is a solid. Right, then we're going to go to the products. We got sodium oxide, and oxides are insoluble except for the alkali metals. Okay, so it's aqueous. Or you could look up here and say sodium is aqueous, and there are no exceptions to that. So this would be aqueous. Then for the lead 2 nitrate or plumbous nitrate, I'm going to look over here and I'm going to say nitrates. Nitrates are aqueous. Are there any exceptions? No, there are no exceptions. So that means that this is aqueous right there like that. All right. Now the next thing that we need to do is we need to start the balancing process. So that's what we're going to do next here. All right, so now the next thing that we need to do is we need to actually balance this equation. So how we balance is the following. We can write what are called stoichiometric coefficients in front of formulas. Okay, and there is no direct method that's the easiest, if you will, but you can do balancing via a variety of different ways. So you can do it by inspection, just looking at it and going, oh yeah, numbers go here. Or you can do it in a methodical way. I like to do it in a methodical way. And I find that probably the easiest way to balance reactions is to find the most complicated formula with the most unusual number of elements. That would be right here. It has lead in it, and it has lots of nitrogens and oxygens. It has 1 lead, 2 nitrogens, and 6 oxygens, because this is a multiplication here, because it's distributed. So 1 lead on the product side, 1 lead on the reactant side. The leads are balanced. 2 nitrogens on the product side and 1 nitrogen on the reactant side. So what I'm going to do is I'm going to place a 2 right here in front of the sodium nitrate. This 2 is distributed over all the terms within that formula, and then there's a hard stop when you hit that plus sign. So there's actually 2 sodiums, 2 nitrogens, and 2 times 3, that's 6 oxygens. 2 times 3, that's 6 oxygens. Okay, but it's really 2 times 3, 6 oxygens plus 1 oxygen. So 2 times 3, that's 6 plus 1 oxygen. And there are 2 sodiums. There's 1 lead, 1 lead. Looks like this is balanced. Now, I won't do this on the other ones, but these are assumed to be coefficients of 1s here. So what I will do is on future problems, I will not write the 1 stoichiometric coefficients. Okay, so this problem is done. Complete, done. We are good to go. We're going to move on to the next problem. I won't write these 1 stoichiometric coefficients. These coefficients are distributed all over all the terms that are inside there. And your final thing that you're going to do on every single one of these problems is you're going to check to make sure that you have the correct answer. And it's really easy to do that. That is that both sides must have the same number of each element on both sides. All right. All right, so let's move on and let's see if we can do the next problem, number 2. So we'll move this on up here and let's hit number 2. it says silver iodide is transferred to a beaker containing an acidified solution of ferric carbonate. So is transferred to a beaker containing an acidified, and then we're going to highlight solution of, and then ferric carbonate. So we have silver iodide and ferric carbonate. Those are the important things. So silver iodide, this is a periodic trend, okay, and silver is right here. It's a +1 charge. Iodide is a halide ion. That's a -1 charge. So I'm going to write that down. That's Ag 1+, I 1-. And then I'm going to find ferric. Notice that it has the IC ending. Okay, and ferric is one of, here we go, is one of these 5. There it is. That's iron, which is ferric. And we have either ferrous or ferric, and ferric is the 3+ charge, otherwise known as iron Roman numeral 3. So I use the common naming, so that would be Fe3+ for the common naming ferric. And then carbonate. Carbonate is a polyatomic ion. And again, I'm going to mention that you do need to know and have memorized your polyatomic ions. And it just so happens that carbonate is a 2- charge. And that would be right here as carbonate. There's the word carbonate and CO3 2-. So I'm going to assume that you have these memorized because that's critical. And that's coming from the unit on nomenclature. So carbonate, CO3 2-. And like I had mentioned on the previous problem, what you do with this is you take the absolute value of these numbers, take the absolute value of these numbers, take the bull by the horn, flip, bring it down. And so you should get AGI parentheses plus Fe2 CO3 in parentheses with a 3 outside. Okay, these are the 2 reactants right here. And you should see also that we have added a cation and an anion, a cation and an anion, and this is characteristic of a double displacement or a double replacement reaction, where we will get a California and a California, that's cation, anion on the product side. So again, these are the reactants, and these will be the products. Okay, and in order to come up with the products, we're going to do the same thing that we did before because this is a double displacement, double replacement reaction. So the silver is going to combine with the carbonate, and then the ferric is going to combine with the iodide. So the silver carbonate, I'm going to take the absolute value of these numbers and take the bull by the horn, flip, bring it down, and I'm going to get Ag2CO3. That is silver carbonate, plus ferric iodide. And notice that the iron comes first because it's a cation, because we're in California. You know, if you're in Georgia or Washington or another state, you can still understand that California will work here for this, a cation, anion. So ferric iodide, Fei and a 3, and then a parentheses like that. Now what we're going to do is, now that we have our reactants written and our products written, now what we're going to do is refer to solubility rules to come up with what states of matter these are. So this first one is silver iodide, and that is iodides are soluble except for silver, mercurous, and plumbus. So that means that this is a solid. And then I'm going to refer back over here, and it says ferric carbonate, it's a solution, and that means that this is aqueous. So whatever it tells you, and it really is, you need more information. It's an acidified solution. That means it's aqueous. That's why that's aqueous. But if you were not given that solution, then you would think that carbonates are insoluble, and the exceptions to that are ammonium ion and the alkali metals, group 1s. Of which that's not. Normally that would be a solid. Then we have silver carbonate. So we'll come back over here, and carbonates are insoluble except for ammonium ion and alkali metals, of which silver carbonate, silver is not, so this is a solid. Then we have ferric iodide, and we'll come over here to our solubility rules, and iodides are soluble except for silver, mercurous, and plumbus, and so that's not one of those, so this is aqueous. All right, fantastic. Now we've got that handled. So what we're going to do now is we are going to balance this here. So we're going to write stoichiometric coefficients in front of formulas. Okay, And in order to do this one, we are going to start off with the most complicated formula with the most numerous amount of elements in it. And that is hopefully, obviously, the ferric carbonate. That's this on the reactant side. So what we're going to do is we're going to take a look at all the components that we have here. We have 2 irons, so I'm going to place a 2 in front of the iron iodide over here. And then I have 3 carbons, and there's 1 carbon here, so I'm going to place a 3 right over there like that. That will give this a 1 coefficient here. And then we have 9, that's 3 times 3 oxygens, and 3 times 3 oxygens, that's 9 oxygens. So the oxygens are balanced. Then we're going to count up the number of silver and iodine. So 3 times 2, that's 6 silvers, and 2 times 3, that's 6 iodines. And so I'm going to place a 6 right here in front of the silver iodide, and now that will be balanced. So your next step is to check and make sure that it's balanced, of which it is. Perfect. Now it's time to move on to the next problem. So we'll do problem number 3 here, and you can kind of see some of that already set up for you. So let's move this on up there a little bit so you can just see what we need to see. All right, fantastic. So this next one is isopropanol. And I gave you the formula. So isopropanol is a rubbing alcohol, or 2-propanol would be the scientific name, 2-propanol, or isopropanol. And this is what's at the doctor's office. And they, rub your arm with a cotton ball or something like that. And it feels like it's very cool because it has a low boiling point and it's evaporating right off your skin. So it says isopropanol, C3H8. And it is poured. And from those other previous things that I mentioned, you should understand that isopropanol is actually a liquid. This is not following solubility rules of any kind, okay? Is poured. That's hopefully a key to let you know that it is a liquid on a watch glass, who cares, and is burned completely. So burned completely lets us know what type of reaction this is. And so the type of reaction is a combustion reaction. So a combustion reaction, and we're going to assume that we have a complete combustion reaction on all the reactions that we're going to do. So not an incomplete, but a complete combustion, okay? The other reactant for every single combustion reaction of which we will be following will have the other reactant, which is molecular diatomic oxygen, and that is a gas. We're going to have an arrow, and we're going to have a delta above this. That is a triangle. That is the Greek letter delta, and that means that heat must be inputted into this reaction like a spark, a match, or something like that in order for this reaction to proceed forward to products. So these are the 2 reactants, isopropanol and oxygen. You need oxygen for every kind of combustion reaction. And again, if we have a complete combustion, then the products are the easiest ones to write for these, and that is carbon dioxide, which is a gas, and water. And we're going to write that as a liquid. Now, the water could be a gas as well, depending on how much heat is released in this reaction. In different types of combustion reactions, you'll have either this as a liquid or maybe even partially gas. So combination of both. All right. And for a combustion reaction, you are going to balance in this following order: carbons, hydrogens, then oxygens. So you're going to first balance the carbons, then the hydrogens, then the oxygens. That's how you're going to do this. Okay. So carbons, there are 3. So there's 1 here. So I'm going to place a 3 right here in front of the carbon dioxide. Then the oxygens, there is 8 here on the reactant side, and I have 2 on the product side. So I'm going to place a 4 right here on front of the water. Then what we're going to do, how we do this, is we're going to count up the number of oxygens that are right here. That's 3 times 2, that's 6. And then we're going to count up the number of oxygens that are right here. That's 4 times 1, that's 4. We're going to add these 2 numbers up, that equals 10. So effectively, this is going to be 10 is equal to, that arrow is an equal sign. And I have my molecular oxygen there. I'm going to call that X plus 1. Here's the 1 right there. So 1 plus X is equal to 10. What is X? X is equal to 9. So X is equal to 9. Hopefully you've done that math okay. So that is an odd number. If it's an odd number, I'm going to use that odd number over 2. And so now my equation is actually truly balanced at this point, and most teachers, instructors, professors prefer having whole number stoichiometric coefficients, and I'm going to assume that. So you cannot end with 9/2 here. So what you're going to have to do is distribute a 2, and that is a 2 over all the terms here. So we're going to end with stoichiometric coefficients as a 2, a 9, 6, and an 8. And then that equation will be balanced right there. And that, again, is a combustion reaction that follows that pattern there, and hopefully that makes sense for you. All right, let's move on to problem number 3. But just a quick little advertisement here. I am the Crazy Hat Chemist, and please watch my videos on YouTube. If you are finding out that you are actually learning something here, then please give me a thumbs up and subscribe to my YouTube channel. And if you know of anybody else that needs some help in chemistry, then most certainly have them subscribe to my YouTube channel as well. All right, so let's move on to problem number 4. So problem number 4 says pellets of sodium hydroxide are transferred to an Erlenmeyer flask holding sulfuric acid. Okay, so pellets kind of indicates the state of matter, okay? And sodium, as we mentioned before, is a group 1. And then hydroxide is a polyatomic ion, that's OH1 minus. And now we get into nomenclature with acids, and sulfuric is coming from sulfate, the polyatomic ion sulfate. So the polyatomic ion sulfate is SO4 2 minus, and all acids in these types of acids that we're going to be discussing have hydrogen ions. So again, what we're going to do is we're going to take the absolute value of these numbers, flip the numbers, bring them down, and you should get NaOH, parentheses for our state of matter, and then H2SO4, parentheses, and an arrow. Okay, and we're going to write down the type of reaction of which this is, and this is a double displacement or a double replacement reaction. You can see that this is combined with a cation, anion, and pellets. So that means that this is a solid, and all acids, for our purposes, are going to be aqueous. You do need to be watching my video playlist series on the acid nomenclature so that you understand this nomenclature and how to write that formula as well. It is a double displacement, double replacement reaction, so I will end up having 2 Californias on the product side. That is a cation-anion combination. Okay, so that is the sodium is going to combine with the sulfate, and I'm going to get Na2SO4, parentheses, plus HOH. All right, parentheses. All right, so states of matter for our product. So anything with sodium in it is aqueous, so that means that this is aqueous. This is actually H2O, and you could have written this as H2O. This is water, of course, and water is a liquid. That is not following your solubility rules whatsoever. It's just, that's a liquid. All right. So now what we need to do is balance this. We're going to start off with the most complicated thing, and that is this sodium sulfate. And there are 2 sodiums. There's 1 sodium on the reactant side, so I'm going to make it so that there are 2 sodiums on the product side. Okay, and let's see, now we need to balance everything else. There's 1 sulfur and 1 sulfur. There's 2 times 1, that's 2 hydrogens plus 2 hydrogens. So that's a total of 4 hydrogens. And there are 2 hydrogens here, and I need 4, so I'm going to place a 2 right there. The number of oxygens, to double check, is 2 plus 4, that is 6. Here's 4 plus 2, that's 6. This is balanced here, and that is problem number 4. So we're good to rock and roll with that one. Now what we're going to do is we're going to move on to our next problem, number 5. Okay, number 5. All right, fantastic. Number 5 is right here. It says a small piece of sodium metal is dropped into a beaker containing aqueous ferrous chloride. Okay. All right, so sodium metal, that's Na, and that is a solid because it's an element. Notice that there is no charge to this. Some instructors might say that this has a 0 charge, of which is correct. Okay, plus aqueous ferrous chloride. So ferrous is Fe2 plus, and chloride is Cl1 minus. And this is coming from periodic trends here, and that is ferrous. I'm going to come back over here to this, and ferrous is the 2 plus charge. And the chloride is right over here as a 1 minus. So that's why I'm getting this. And so then I'm going to write that down, FeCl2. And it says that it's aqueous, and that would be aqueous right there like that. And the other way that you could do this is follow the solubility rules, and you should get that this is aqueous. That is, chlorides, bromides, and iodides are aqueous except for silver, mercurous, and lead, and therefore iron is not one of those. So of course it would be aqueous. All right, so this has a different pattern than the previous 4 problems. And so this is an element all by itself in its standard state. And then this is a California. That's a cation-anion combination. So this is characteristic of a single displacement or a single replacement reaction. Okay, and that is you need to consult an activity series, and sodium is very reactive and it will displace iron, and then you get iron on the product side, Fe, and this will be a solid, which would have a 0 charge there for everybody else that needs that. Then you're going to combine the sodium and the chloride that are going to get together. Well, what is the periodic trend of a sodium ion? And that's a 1 plus because it's in group 1. And so I'm going to combine the sodium ion with the chloride ion, and that will be NaCl, like that. And here we go. We're going to come up with the state of matter for sodium chloride based on our solubility rules, and that is anything with sodium in it is aqueous. So we're going to write aqueous there, just like that. All right, now what we need to do is balance this. This is probably the most unusual formula here. Oh, by the way, for a single displacement, single replacement reaction, you get an element and a cation anion. So the pattern on the reaction side and the pattern on the product side is the same, just like on a double displacement reaction. Okay, I'm hoping that you see that there's a noticeable difference between a double displacement and a single displacement. So I'm going to pop in this double displacement reaction that we just did. That's a cation-anion for a double displacement, and an element cation-anion for a single displacement. The products are the same for the double displacement that you got for the reaction side, and that's the pattern is cation-anion. And again, the products for a single displacement are the same as what's on the reaction side, and that's an element cation-anion. Okay, hopefully you can see the distinct difference and a little bit of a similarity between the two. All right, moving on up back again so that we can actually balance this in problem number 5. And this is our most complicated formula. There's 1 iron, 2 chlorines, and 1 chlorine. So I'm going to place a 2 right here in front of sodium chloride, and that gives me 2 sodiums, and that has 1 sodium. So this will be 2 sodiums right there like that. So now that one is balanced. All right, so that is number 5. Let's move on to number 6. All right, so let's slide this up there a little bit so we can just focus on number 6. All right, number 6, it says 4 mils. Who cares how much of sodium bromide? That's going to be important. Okay, solution maybe is transferred into a beaker containing 5 mils of, and then phosphoric acid. All right, so sodium is a group 1, and that's a 1 plus. Bromide is a halide ion, that's a 1 minus. Phosphoric acid is coming from phosphate, that's PO4. 3 minus, it's an acid, and it will have hydrogen ions associated with it. Okay, so I'm going to take the absolute value of these two numbers, flip them, bring them down, and I'm going to get NaBr, that's sodium bromide, plus absolute values, flip these numbers, and I'm going to get H3PO4, parentheses. Okay, states of matter. anything with sodium in it is aqueous. Even though it did say solution, it didn't really matter. And this is an acid, so that's aqueous. This is a cation, anion, and a cation, anion. So this is characteristic of a double displacement, double replacement type of reaction. In order to get my products, I'm going to combine the sodium with the phosphate. So that would be Na3PO4, parentheses. And then the H and the Br. And that is take the bull by the horns, flip, bring it down, HBr. I'm going to look at my solubility rules to come up with the states of matter here. Anything with sodium in it is aqueous. And this is hydrobromic acid. So this is an acid, and that is aqueous. All right, now what we're going to do is we're going to balance this. We're going to start off with the most complicated formula, which is probably this sodium phosphate. And so there are 3 sodiums. There's 1 sodium. I'm going to put a 3 right here. There are 3 bromides and 1 bromide. I'm going to place a 3 right there. That gives me 3 hydrogens, and there are 3 hydrogens, 1 phosphorus, 1 phosphorus, 4 oxygens, 4 oxygens. I'm good to go. This is a cation anion, and this is a cation anion. So those are characteristics of a double displacement reaction. All right, hopefully that works out well for you. Now we're going to move this piece of paper on up and slide it up to problem number 7. Let's see, here we go, problem number 7. All right, a little quick station break. Remember, you are watching the Crazy Hat Chemist, and please watch my videos on YouTube. And if you are learning something from this, I would appreciate you giving this a thumbs up, because I am ultimately trying to be your teacher for chemistry so that you can perform well in college and beyond. All right, so it says a solution of aluminum sulfate is added to an aqueous calcium hydroxide in a round bottom flask. All right, so again, I've crossed out some words that you can cross out, don't really matter, and all that kind of stuff, and left some words that do matter. So aluminum sulfate. So aluminum is a periodic trend charge of a 3+. And then sulfate is a polyatomic ion. That's SO4 2-. Again, remember, I am assuming that you do know your periodic trends. And that is a silver 1+, zinc 2+, aluminum. There's my 3+. And of course, sulfate is a polyatomic ion. So you just have to flat out memorize that. And then it says calcium hydroxide. Calcium is a group 2, so that's a 2+ charge. Hydroxide is a polyatomic ion, a 1- charge. I'm going to take the absolute value of the numbers, flip them, bring them down, and I get Al2SO4 parentheses and a 3. It says it's a solution, so we're going to write aqueous plus Ca parentheses OH and a 2 and parentheses, and it says aqueous, so we're going to write AQ. This is a cation and an anion and a cation and an anion, so this is double displacement, double replacement type of reaction. I want to make a quick little note here, and this is a really common error in writing calcium hydroxide without the parentheses, and that would be incorrect. Okay, that's one of the most common errors that students make, is not having the parentheses around hydroxide, because you can clearly see it with this 4 here with the sulfate that you need the parentheses for, but for some reason students mess up the parentheses around hydroxides when you have more than 1. Anytime you have more than 1 of a polyatomic ion, you're going to have that number down there, unless it's reduced, of which it is not in this case. So again, look at my nomenclature unit. Okay, since this is a double displacement, double replacement reaction, we're going to write our products, and it will be aluminum hydroxide, and that is Al parentheses OH, and look at that, there's a parentheses around that OH. All right, and then it will be calcium sulfate, and notice that calcium and sulfate both have a 2 charge, so that's going to reduce to CaSO4. Okay, all right, now what we're going to do is we're going to look on our solubility rules, and at the very bottom of our solubility rules, are hydroxides, and hydroxides are insoluble except for the alkaline metals and ammonium ion, of which this is not, so this is a solid. And then calcium sulfate. So over here, we have sulfates. Sulfates are soluble except for barium, strontium, lead, calcium, and calcium is slightly soluble. So that means you could write either AQ or you could write S. There is more to that, but we'll just let that go for the moment, okay? All right, so now we're going to balance this. This is probably the most complicated formula by far. There are 2 aluminums on this reactant side. I'm going to make 2 aluminums on the product side. There are 3 sulfurs on the reactant side. I'm going to make 3 sulfurs on the product side. There are 3 calciums, and I'm going to place 3 in front of the calcium hydroxide there. You should be able to check the oxygens and the hydrogens on your own. I'll let you do that, but it is balanced. All right. That's number 7. So let's move on to number 8. Moving the page here so we can go on to the next problem here. Right. So where's number 8? Here we go. Here's number 8. It says shavings of magnesium is added to powdered ferric oxide and warmed slightly. Okay, the warmed slightly really doesn't mean anything for you. It just means that this reaction does go forward to completion. So magnesium, and it says shavings. So that would be that this is a solid. Oops, no arrow, plus sign. And then ferric oxide. So ferric is Fe3 plus and oxide is a 2 minus. Both of those are periodic trends. So I'm going to have Fe2O3. And it says powdered, so that means that that's also a solid. So hopefully that makes sense on those. Okay, this is an element and a California that is a characteristic of a single displacement or a single replacement reaction. That is, magnesium is more reactive than iron. It will push it out of the way, and you're going to get iron as an element that will be a solid all by itself. And then magnesium and oxide will get together. So you're going to have this characteristic pattern of element and cation, anion. And so magnesium is a group 2, that's a 2 plus charge. Oxide is a 2 minus. So I'm going to take the bull by the horns of both of these, flip them, bring them down, and then reduce. And that's how I get MgO. Okay. And then we're going to refer to our solubility rules to get the MgO. And that is oxides are insoluble except for ammonium ion and the alkaline metals. That is not an alkaline metal, that's an alkaline earth metal. So that's a solid. All right, single displacement reaction. Now what we're going to do is balance this. Probably what we're going to do is we're going to look at the most complicated formula that's right here with the ferric oxide, otherwise known as rust. There are 2 irons. I'm going to place a 2 in front of the iron. There are 3 oxygens, 3 in front of the magnesium oxide, 3 magnesiums, 3 magnesiums. And now we're balanced. Okay, so hopefully that one worked out well for you, number 8, and we're good to go. All right, cool. Let's move on to number 9. All right, number 9, it says aqueous ammonium hydroxide is added via a burette to a flask of sulfuric acid. All right, so ammonium hydroxide is ammonium is this polyatomic ion. You have to know this polyatomic ion. It is the only polyatomic cation, so that's why it's very important. Hydroxide is a polyatomic ion. There we go. Sulfuric acid, we have done sulfuric acid previously in this because, but that is coming from sulfate. That's SO4, 2 minus, and it's an acid, so that's a 1 plus for the hydrogen. All right. Take the bull by the horn, flip, bring it down. I get NH4OH. That's ammonium hydroxide. And it does say that it is aqueous. So we'll write aqueous right there. Plus H2SO4. And this is an acid, so it is going to be aqueous. By the way, you did not need ammonium hydroxide to say aqueous at all. You actually could have just looked at your solubility rules and said, oh, anything with ammonium ion is aqueous. Anything with ammonium ion is aqueous, and you're ready to rock and roll. And all acids are aqueous. Okay, this is a cation anion. So this is double displacement, double replacement reaction. So I'm going to get a cation anion and a cation anion. I'm going to combine the ammonium ion and sulfate. Take the bull by the horn, flip, bring it down. So NH4 parentheses 2 SO4. And as I just mentioned, anything with the ammonium ion in it is aqueous. Okay. And then I'm going to have these two get together, and that is going to be HOH, and that is otherwise known as H2O, right? And that is also going to be a liquid. That is nothing to do with anything but as far as solubility rules, okay? It's just water. All right, now what we're going to do is balance this. We're going to start off with the most complicated formula. That's right here with the ammonium sulfate. There are two nitrogens. I'm going to place a 2 in front of the nitrogen right there. This gives me two oxygens here, plus the 4. There's already the 4 here, and there's only 1. So I need to place a 2 right here. And then I'm going to leave it to you to check the number of hydrogens and the number of oxygens, but I guarantee you they are balanced right now. All right, let's move on to number 10. So let's slide this baby on up here to number 10. Number 10, it says solid aluminum oxide is heated in a crucible in the absence of air. Okay, so aluminum is a 3+ charge. That's a periodic trend. Oxide is a 2- charge. That is also a periodic trend. I'm going to put these two things together, take the bull by the horn, flip, bring it down, and I get Al2O3. And it says it's a solid, so I'm going to write that there. And then it says in the absence of air. Well, you know, when you're absent from school, are you there? No, you're not there. So that means that there is no other reactant, and it's heated. So that means that this is a delta, a triangle. This is characteristic. This is the easiest type of reaction to identify what the reaction type is. And that is when there is only one reactant, it is a decomposition. So there's a decomposition reaction. And on a decomposition reaction, what do you get on products? You get a gas plus a cation anion or an element. Those are the possibilities that you get. You're going to look over here and on the reaction side and figure out what kind of gas would you get. The gas which you would get would be oxygen. That is diatomic. And typically the gases that you're going to get for the reactions are either oxygen, carbon dioxide, or sulfur dioxide. So since there's no sulfur or carbon, you cannot get carbon dioxide or sulfur dioxide. So you have to get the oxygen. And then plus. And if there was an alternate charge for aluminum, of which you look on your periodic table and you go like, oh, there is only one charge for aluminum. There is no other charge for aluminum. So that means that aluminum cannot combine with the oxide in any way, shape, or form, except for by itself. That means that we are going to have aluminum that is a solid as an elemental state. All right. Cool. Now what we need to do is balance this. So we have two aluminums. Most would put a 2 in front of the aluminum, but we're going to have to rebalance this in just a moment if we do that. There are 3 oxygens and 2 oxygens. So we're going to multiply those two numbers together, 3 and 2, 2 and 3, and we're going to get 6. So we're going to have 3 there. That would be 3 times 2, that's 6. And then 2 here, that's 2 times 3, that's 6. Now we have 4 aluminums. 4 aluminums, and now, boom, that is balanced. Fantastic. Now what we're going to do is we are going to move on to the next problem here. That is problem number 11. We've done 10 problems already. That's pretty remarkable. I'm hoping that you are following along and learning some cool chemistry. Okay, so here we go. Number 11. Let's slide this on up here. Here we go. Perfect. So it says chemistry teachers like to fish by throwing a block of sodium into a river from a bridge. Hint, right reactant as a Ca, that's cation anion. So sodium is an element and its state of matter is a solid. And a river is composed of water, and so the formula for that is H2O. However, it says in this as a hint, you're going to write it as HOH. Okay, and that is a liquid. Notice that this is an element and a cation anion. You can clearly see the cation anion combination here in this, and this is characteristic of a single displacement or a single replacement type of reaction. Okay, now anytime, so I gave you the hint on this problem, but now you know. So now that you know, anytime that you have water as a reactant, you are going to write it as a cation anion combination. You are not going to write it as H2O. If it's a product, who cares? You can write it as H2O. But as a reactant, you're going to write water as HOH. That will help you identify what you can do with this and see that there's a cation and an anion clearly. Sodium is more reactive than hydrogen. It will displace the hydrogen. And now you're going to get hydrogen. What's the formula for hydrogen when it is an element by itself? Well, it is H2, and that is a gas. Hopefully that makes sense. It's one of the 7 diatomics. Okay, and then the sodium is going to combine with the hydroxide. Hopefully you've seen, if you've done cation, anion, instead of the H2O, then you can see that it's the sodium and the hydroxide that are combining together. Sodium is a group 1, hydroxide is a polyatomic ion of -1, so it's NaOH. Okay. And what really, anything with sodium in it is aqueous, so I'm going to write aqueous for this. All right, and so now we have our characteristic pattern of a single displacement. That's an element and a cation anion on the product side. So hopefully that works for you. Now what we need to do is balance this. So everything is balanced except for the hydrogens. There's one sodium, one oxygen, and there are 2 hydrogens and 1 plus 2, that's 3. So I need 1 less over here. So I could put a 1/2 coefficient in front of this and then multiply the entire equation by 2. And then I will get a 2, a 2. This becomes a 1, and this is a 2. And that is problem number 11. Again, quick little advertisement, that is, you are watching the Crazy Hat Chemist. Please watch my videos on YouTube. In fact, you're watching this video on YouTube, then you're watching my YouTube channel. Please subscribe, send this to all your friends who need to learn and understand chemistry, because I am your chemistry source for college prep chemistry, or even first-year college chemistry on my AP Chemistry unit series. All right. Next problem, here we go, is powdered. That's letting you know it's a solid. Chromic carbonate is heated in an evacuated oven. So chromic, Cr3 plus, carbonate, CO3, 2-. That's a polyatomic ion there of the carbonate. So I'm going to combine those two things together. Cr2, CO3, parentheses, and A3. And it says it's powdered, so that means it's a solid. It's in an evacuated oven. That means that there is nothing else. This is a compound all by itself. There's only one thing on the reactant side, so that means that this is a decomposition. So characteristics of a decomposition is I am going to get a gas and a cation anion combination. So as I had mentioned, the gases that you could possibly get would be either oxygen, carbon dioxide, or sulfur dioxide. Do you see sulfur in here? No. Do you see carbon in here? Yes. And do you see oxygen? Yes. So you're going to get carbon dioxide. That is a gas. Okay. Then we need to find a cation anion combination, and we're going to have the chromic come together with the remaining amount of oxygen. So it would be chromic oxide, and that's Cr2O3. That's chromic, and that's a plus, and oxide, that's a 2-, and you should see that formula. This is a decomposition reaction, and on decomposition reactions, you are not looking at solubility rules, so that is a solid there as well. This is a 2 right there. Hopefully that's good. All right, so now what we're going to do is we're going to balance this, and we have, let's see, two chromiums. We have 3 carbons, and there's 1 carbon. So I'm going to place a 3 right here in front of the carbon dioxide. That will give me 3 times 2, that's 6, plus 3, that's 9 oxygens. 3 times 3, that's 9 oxygens. Oh my gosh, that's balanced. We are good and rocking and rolling. All right, so let's cruise this on up to number 13. Lucky number 13. I love number 13. Number 13 is actually my favorite number. Why? Well, I'm in room 13. So that's probably why. All right. So it says 1 gram of shavings. Who cares if it's 1 gram of calcium hydroxide are dropped into a beaker containing 2 molar phosphoric acid, because it doesn't matter the concentration of the phosphoric acid. So calcium is a 2+, hydroxide is a polyatomic ion, 1-. Phosphoric is coming from phosphate, that's PO4, 3-. It's an acid, that's hydrogen. Okay, and you should kind of recognize this one here. So I'm going to get Ca parentheses OH and a 2, and it says shaving, so that means that this is going to be a solid. Plus H3PO4, and this is an acid, so this is going to be aqueous. I combine these together, and then cation, anion, so this is a double displacement or a double replacement type of reaction. Okay, and so I am going to combine on my product side the calcium phosphate together, and then the hydrogen and the hydroxide. So calcium phosphate. This is obviously the most complicated formula, plus the HOH, which is H2O. I can write it HOH or H2O, and that is a liquid not following solubility rules whatsoever. That's just is what it is. Water is a liquid, unless otherwise stated. And then calcium phosphate, we get our solubility rules, and that is phosphates are insoluble. Exceptions to this are ammonium ion and the alkali metals, of which this is an alkaline earth metal, so therefore this is a solid. Cation, anion, and this is obviously double displacement. Now what we're going to do is we're going to start off with the most complicated formula. Obviously, that is right here. And that's 3 calciums, 1 calcium. So 3 calciums now. And then 2 phosphorus and 1 phosphorus, 2 phosphorus right there. Now what we need to do is balance the oxygens and the hydrogens. So here's a hint here. This is kind of a little complicated one. There's oxygens, 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 and oxygens. So there's oxygens in every single formula. Then there are hydrogens, no hydrogens, and hydrogens. So what we're going to do is we are going to balance the hydrogens, and the oxygens will have to come along for the ride. So how many hydrogens right here? That's 3 times 2 hydrogens, so that is 6 hydrogens. How many hydrogens here? 2 times 3, that's 6. So 6 plus 6, that is equal to 12. No hydrogens here. I need all 12 hydrogens to be going here. So that is going to be a 6 times 2. That is 12 hydrogens. So I'm going to balance, or actually, sorry, confirm the balancing that I just did with the oxygens. And that is 3 times 2 oxygens, that's 6. 2 times 4 oxygens, that's 8. So 6 and 8, that's 14. And then 2 times 4, that's 8, plus 6, that's 14. So boom, we're balanced. We're rocking and rolling. We're pretty good right there. I like that. All right, now we're on to number 14. So let's slide this paper on up and let's do number 14. Here we go, number 14. It says an aqueous solution of aluminum sulfite. An aqueous solution, oh my gosh, look at that, it's there twice, is added dropwise to a solution of calcium hydroxide. So that solution or aqueous lets you know that it's a solution. Aluminum is a 3+ charge. Sulfite is a polyatomic ion, that's SO3 2-. And then calcium is a group 2+1, and hydroxide is a polyatomic ion, just like that. So here we go. Absolute value of these two numbers. Take the bull by the horns, and I get AL2. So 2 parentheses SO3 parentheses and a 3, and it says that it's a solution, so that means that this is aqueous. Okay, plus calcium hydroxide, absolute value of these two numbers, tick the bull by the horns, that's Ca parentheses OH and A2, and that is again a solution, so this is aqueous. Type of reaction, this is a cation anion, and that is double displacement, double replacement characteristic of that. So I will get cation anion and a cation anion over here. I'm going to combine the aluminum with the hydroxide, and that will be Al parentheses OH and A3. And then I'm going to combine the calcium and the sulfite. Notice that they're in the same ratio of 2 to 2, so the 2's disappear. I'm going to have CaSO3, and then I'm going to put parentheses for my states of matter. So aluminum hydroxide, look at my solubility rules, and that is hydroxides are insoluble except for ammonium ion and alkaline metals, of which this is not. So this is a solid. And then calcium sulfite. And I don't actually have sulfites on here, but this is actually going to be a solid as well. And it kind of follows these rules. And that is the sulfate rules are right here. Sulfites and sulfates are very similar. And it says slightly. So we're going to say that this is a solid. All right. Now what we're going to do is we're going to balance this baby. We're going to look for the most complicated thing that's obviously right here. I got 2 aluminums. I'm going to place 2 in front of that aluminum. I got 3 sulfurs, and I'm going to place a 3 in front of that. That gives me 3 calciums, and that's 3 calciums. And you're going to double check with the number of oxygens and hydrogens, but they will be balanced with this as well. All right, perfect. That is number 14. All right. Now what we're going to do is slide this baby on up. I'm going to slide this baby on up here a little bit more here so that we got problem number 15. Okay, and before we carry on with problem number 15, remember, I am the Crazy Hat Chemist. You're watching me on YouTube, and please subscribe to my YouTube channel. Pass it on to all your friends. Pass it on to your grandmother, your grandfather, your aunts, your uncles. If you have anybody, friends in other countries, pass it on to them. Maybe they might need some good chemistry assistance as well. All right. A flask containing molecular nitrogen. So that is going to be N2. And that is a diatomic, it's nitrogen, and that is a gas. Plus is opened and powdered magnesium. Powdered magnesium is transferred into it. Magnesium powdered. That's a solid. I'm not looking at solubility rules here whatsoever. Okay, so we haven't done one of these types of reactions. It does not follow the characteristic patterns of a double displacement or a single displacement or a combustion. So it's a combination. So it's not double displacement because it doesn't have a cation anion. It doesn't have a single displacement, doesn't have a cation anion. It's not a combustion, and it's not one compound, so it's not a decomposition. So this is a combination reaction. I'm going to combine these two things together such that the cation comes first, because we follow the cation anion rule. The cation is magnesium, and magnesium on our periodic table is a 2+ charge. Nitrogen is the anion, and that is a 3- charge. So I'm going to take the bull by the horns, bring it down, and I am going to get Mg3N and a 2. And that's going to have to be a solid because it's a combination reaction here. So now what we're going to do is we're going to balance this here, and we have 3 magnesiums, 2 nitrogens, boom, it's a pencil job, and I think we're good to go. Hey, I am going to pause right here. We have many more problems to do. We have up to 36 of these types of reactions, and then there are 10 more of doing net ionic equations. So I'm going to give this a pause right here, and this will be part 1 of how many parts I don't know because I haven't. So this will be part 1. I'm going to pause this video here, and then you're going to have to go for the next video for the next set, starting with problem number 16. All right, I'm hoping that you're learning lots of good chemistry here. I am the chemistry instructor that you're going to go to learn your chemistry. All right, I'll see you for part 2. Bye for now.